In task number 3, we are going to investigate the monotonicity and extrema of the function, of the given function. So as you remember, it is necessary to use the first derivative, the sign of it, and then the property, how it describes how the existence of the extrema is implied by the monotonicity, changing monotonicity of the function. Okay, so we start as usual with the domain of the function. This function has a real domain, so nothing wrong happens here. So next we need to calculate the first derivative of the function. So first of all, we notice that our function is in the form of the product, so we need to apply the rule for the product. So it will be minus 2x prime e to the power minus 4x plus minus 2x squared times derivative of e to the power minus 4x. Okay, so the first derivative is extremely easy, so nothing to comment. And here we have the box rule. So we need to remember not only that e to the power of x gives the derivative of e to the power of x, but also multiply by the derivative of the exponent. So finally we have such expression, minus 2x squared times e to the power minus 4x and times minus 4. We see that there is the common factor. It is always worth to write the final form of the derivative in the product form, so we'll have minus 4x plus 8x squared in the bracket. Okay, next step is to consider the necessary condition to identify the points where the extrema may appear, so where the derivative gives value 0. So we have e to the power minus 4x plus 8x squared equal to 0. And we had a very similar example at the class. We emphasized then that this expression is positive, always positive, so it never gives you value 0. So the value 0 is only when this bracket it can be 0, so let's factorize it. We'll have that minus 4x is multiplied by 1 minus 2x. So this gives you two values, x equals 0 and x equal 1 over 2 as a candidates for the extrema. However, it is not set yet that at those points we have any extremum. For this we need to investigate the sufficient conditions, so the sign of the derivative, first derivative, and check whether it changes in the neighborhood of the function. Okay, so starting from the scratch, we have the same expression, but now we work with the inequality, which behaves differently than equation. This expression, as we noticed, is positive, so for the positive value of the whole expression, we need to have minus 4x plus x squared positive. We already know the 0 points, 0 and 1 over 2. We see that parabola opens upward, so the approximate graph of the sign of the first derivative is like this. So between 0 and 1 over 2 we have negative value, on the left side of 0 we have positive value, and the right side of 0 positive value. Okay, so now making the conclusions. We have the following situation. We have x, a function considered in minus infinity to 0 at point 0, 0, 1 over 2, 1 over 2, and interval from 1 over 2 to plus infinity. This is what we see from this graph. Then we have function f, the derivative positive here, 0 at 0, negative in this interval, 0 at 1 over 2, and positive in the last interval. So now we conclude about function f. In the interval from minus infinity to 0, function is increasing. In the middle interval decreasing, then again increasing. So here at 0 we have local max, and at 1 over 2 we have local minimum, local min. If you want to know what is the value of the function at this local maximum and local minimum, simply you need to calculate the value of the function at those 2 points. So we will have, as you see here, minus 2x squared e to the power minus 4x, so minus 2 times 0 times e to the power 0, which is 0, and minus 2 times 1 over 2 squared times e to the power minus 4 times x, which is minus 2 times 1 over 4 times e to the power minus 2, which is minus half e to the power minus 2. Like this. The typical mistakes with the solution of the inequality, the graph sometimes was made in the inverted way, and more importantly with the derivative. So please revise how to calculate derivative of the product.